Hi, everyone. I had a request a day ago about can we have some kind of, I think the term was idiot proof guide, and not really an accurate term for what we're talking about here, but an idiot proof guide to programming. Can you make programming simple enough that it's step by step that you can follow? And I thought about it. I went, I would really like that. Because, quite frankly, for most programmers, for most academics that are in computer science or have a training in this, they came to this somewhat naturally, much like someone that is a professional pianist probably didn't have to struggle to play Mary Had a Little Lamb. They just they took to it quicker than maybe some other people. But that doesn't mean that not everyone can do it. I can learn to play the piano. I can learn to speak French. I will never be perfectly bilingual, but I can learn to speak French. Mathematics. I swore I was terrible at math. I'm saying past tense. I would be always like, oh, I can't do math. I still say it. It's not actually true. It turns out that I just didn't have enough training in it. I didn't have enough self-confidence with what I was doing. But with enough exposure, I got fairly good at it. Not a mathematician by any stretch, but enough to teach classes in it. Same thing with programming, but a lot of programmers do it naturally and then therefore think there's no natural way to teach it. You can't teach creativity. Oh wait, you can teach creativity. It's not that some people are sort of have a more of a gift, some natural affinity for it, but that doesn't mean you can't teach tactics, skills, traits to make you more creative. I'll also say this is not a recipe. This is not an algorithm, technically. This is way too ambiguous to be an algorithm. You can't algorithmically teach how to program, much like you algorithmically teach math, because the point of it is that you're supposed to think on your feet, that you're supposed to process and deal with different inputs, deal with different problems in different ways. That's the point. And so if you were teaching math and you had just plug and play numbers, I'm sorry to disappoint you if you think what this is. I can't in good conscience teach that. That's not what we do. We don't just say, here's what a pointer is, let's do this. Here's how you do this exact thing, and I'll give you slightly different inputs, and you will give me slightly different outputs. Like what you would in high school. It drove me nuts. It's meant to be how you think about the process, how you think through problem solving. And that's the point of the course even. It's algorithmic thinking. It's not C programming, it's algorithmic thinking, because that's the skill that generalizes to other languages, to other things, to what you do if you're doing technical support, or if you're an IT technician, or if you are just designing something, just any kind of design. It's all constraint-based problem solving. That's what we do. That's what we're really good at. And that's the skill that we're trying to teach you guys. So it is not magic. I will have some guidelines that I think should help, but it ain't magic. It's a series of steps that you take along the way. So here we go. So I break it down first off. I'm going to break it down to 3 steps. There's 3 different parts to the process of coding. Step 1 is easily the most important step out of the whole bunch. It crushes every other step. The other steps are trivial by comparison. They're also the thing that you can't do the other 2 unless you do the first one. And yet that's the thing that everybody drops. Every time I get students that are struggling, that's the thing I find out they didn't do. Almost without fail. It is sort of ridiculous in that way. People are trying to go faster, so they skip step 1, planning. And that's why they fail. They run before they walk, or more importantly, they are not prepping before they do something. They're like, I want to go camping in the wilderness. I don't need to pack my bags. I'm just going to go camping. You're like, no, you're going to get eaten or something, right? You don't just walk into the woods and start walking around. You plan. We need to plan here. So we'll get to that in a second. I just want to cover a little bit of an overview. First of all, we have 3 different steps. I'll go over each one in part, but really, programs work in a series of sequences. Fine, we'll get into that detail in a second. You will make mistakes. Those, by the way, those 2 things, dictate everything we're doing for the rest of this sort of mini lecture, or maybe a full lecture. I don't know how long-winded I'm going to be. And then we have metrics for what makes a good algorithm, a good program. And those ultimately dictate when the end result is. Are you satisfied with whatever you coded? It's not just does it work, it's what makes it good. What's good versus bad. If you're talking about an artistic piece, it's not just did you draw that picture. There's technique. There's things. What are you trying to express in your painting? So there's metrics of quality that we have that we'll look at as well. So the big one, one of the big ones, programs work line by line. That seems trivial. It's not. In fact, that's what trips a lot of people up. It's because it is so simplistic that people think there must be something more. No, it's going to start at my main method. It's going to go line by line. It's going to get to the end of my main method. That's the end of the program. There is nothing else. Line by line until the end of my main method. One function starts, that same function ends, and that's the entirety of my program. Now there's a lot of stuff inside of that. It's like a Rube Goldberg machine, right? You start something off and a whole bunch of crazy stuff happens. But essentially, there's a start, there's an end, and it all gets done in the main. What I do in the main might be to call another function, another bunch of code, do those things. But those are still step by step. And then I come back. And then I go off to another function, do a series of step by steps, and then I come back. There's no, you can predict and plan everything based on the fact you know what the next step is and the next step is and the next step. Much like if I'm building a Lego, right? I don't know if this is a dog or a wolf or a cat or what the heck that's supposed to be, but it's a Lego. Fine. It requires a bunch of pieces, and I go step by step. There's no step in there. There's no put whatever you want in there step. It is step by step, this piece goes here. Step by step, this piece goes there. I might do one series of steps that build one part, like the ear, and another series of steps, maybe not the ears, the tail, legs, another series of steps that build this part, and then another series of steps that do this. That's fine, but it's still step by step. I'm going, the entire thing, the entire Lego booklet that I have is step by step linear instructions. And sometimes it says go and do this next part, and it's a sub part, but it's still all one series, a line with no ambiguity. So my code starts and ends in main. That's it. And sometimes it goes over, it'll jump to another function, another part of code, and do stuff. But it'll tell you when it's going to jump. And when it jumps, it does a series of steps and then jumps right on back. It's just a series of steps. So you can temporarily jump, fine. They're simple and they're unambiguous. That's actually what we do. We build with basic, minuscule building blocks. And then we build more complicated things with those building blocks. Call it a function, like sort of wrap it up and say like that thing will make the tail, or that thing will make a leg for the Lego. Okay, and then I just call that make leg 4 times and I'm good. But it's still one step at a time. What I want is to be able to do these simple, unambiguous steps in a sequence to do something useful. And if that can be general and reusable, that's even better. So I have little parts, but if I put them together, I get a bigger part. I'm composing based on these little tiny parts. So bigger parts from smaller parts. And we'll see that again and again. That's what you're going to see when we talk about functions. I want a widget that does something. This thing finds the minimum value in a list. Great. This thing removes all the letter Q's from a string, or lets me find a particular letter in a string. Great. I can reuse that. But it's still step-by-step linear series of instructions. And I build up to something that make more sense. So I say, this, I'm just going to remove this character from the string. Okay, it seems like one instruction. It's a whole bunch of them, but it seems like one instruction, and I do all of that in one go. I like to point out the fact that making mistakes is just built in. It's baked in to what we do, to the point that before we have computers, before they're even really invented, just the theoretical idea of a computer, they're able to prove that you can't prove that a computer will stop, or that a program will stop. Before we even have a computer, we know that we can't prove things about it, so we don't even try, essentially. We can't guarantee stuff as programmers. It's really kind of depressing. And so baked into the system, what everyone goes through is just like, you will make a mistake. There's no shame in making a mistake. It's actually a shame to not make mistakes to a certain extent. You're going to make a mistake, otherwise you're not trying. Otherwise you're not really pushing things. If somebody ever walks up to me and says like, I've never made a bug in my code ever in my life, I said, you don't know how to program then. You clearly didn't program enough to hit that scenario. It will happen. It will happen repeatedly for guys like me, right? I make mistakes all over the place. That's fine. If you come at it like that and you make a mistake, you don't go, I'm dumb. You go, yeah, par for the course, right? If you go to the beach and you don't get sand in everything, like you don't get sand in your clothes or sand in your towel, you didn't really go to the beach, right? I mean, just it's part of what you expect, even if it's annoying. So you will make mistakes. Don't panic. By the way, Hitchhiker's Guide to the Galaxy reference everyone knows. This leads us to a bunch of other things. One of them is the KISS principle, which applies to a whole lot of other domains too, but this is not rock and roll all night party every day. This is keep it simple, stupid, right? Everyone overthinks. I'm famous for trying to do this, right? You get all cutesy and trying to make some cool program. No. Keep it stupidly easy. Even if it's boring to write, keep it stupidly easy. It'll work. Stop trying to overthink things. Keep it simple. Because we know we make mistakes. And if you don't think you're going to make mistakes, it's going to bite you. Okay. I want to design by concepts because people are not really good at little fiddly things. So I want a thing that does X. I want a function that removes that particular character. I want something that finds the smallest number. Just a widget that I can get my head around. I don't want it to do random stuff. I want it to be like, it does this. It sorts a list. This thing sorts a list. I can get my head around that. I can understand that. Good enough. This finds the smallest, the greatest common denominator between two numbers. Good. I understand how that works. Well, maybe you don't, but if you're a mathematician, you understand how that works, right? This thing does the dot product of a matrix. Something. It does a job. And you know what the job is? You conceptually, as long as you built your code around what your concept you're trying to get across, you're fine. It's not weird interwoven things. And essentially, just don't panic. Oh, it didn't compile. Whoops. It's not you. It's you coding. Everyone does it. Don't worry about it. You'll eventually get through it. It'll fix. Fine. There's no shame in having compilers. There's no shame in having a bug. It's annoying, but it just is. It's what you do. I would also say that every other industry, every other place has that same thing, except for people don't want to admit to it. No one wants to admit that they screwed up or had some problem. You're like, no, every design is wrong as well. If I'm doing a graphic user interface, it's wrong. The first time I make it, it's wrong. Every time. That's not me. That's everybody. The expectation is it's wrong. It might be close to being right, but there's something wrong. And you can improve it. Every time you do anything, you just expect it to be wrong and fix what you find is wrong. It's a very different philosophy. You stop being depressed about, oh, I can't code. No, you expect it to not work. That's fine. It will eventually work. This motivates everything that we do. If you know you're going to make mistakes, now you do things that are defensive. You're doing things that you know are going to prevent you from shooting yourself in the foot. So, if you, like English essay, if you're writing an English essay, you know you're going to have to do another draft afterwards. At least I hope you guys do multiple drafts of any English essay, anything you write. Because it's always wrong. There's always improvements. There's always grammatical errors. There's always a need to proofread. If you go into it like that, it's human nature. You build it, you bake it into the system, how you approach things. Okay, so I have a bunch of visuals and I'll point out what they are mapped to. So we have metrics for what is quality, right? One of them is, I want general things. I don't want some super knife that only cuts avocados. I want a chef's knife, this general purpose tool that I can apply to anything. Not anything, but that's a better, if I have a function or code that is general purpose, it's generally considered better, right? If I can use it for a whole bunch of different things, fantastic. I don't want something that is very niche, very specific. I have an avocado pitter downstairs. I use it once every 4 weeks or whatever, when you have, not avocado, mango pitter. Every 4 weeks you get a mango and slice it. Oh, whoopee-doo, right? It's taking up my drawer space. I want functions and code that I can reuse if I can. Okay. The Donald Duck, sorry, not Daffy Duck. Sorry to offend anyone here. The Donald Duck here. Worry about scale. This is a computer science thing. Every 18 months, the size of our data doubled. Every 18 months for years, until 2006 or something like that. And even now, it's still pretty close to that. Every 18 months, the size of your hard drive doubles. The amount of things you could do doubles. And the amount of crap people throw at you doubles. Nothing else does that. And as a result, that's what we're constantly paranoid about. The Google interviews are just about this, essentially about this. How do you handle scale? So we're not going to worry that much about scale, but normally it's like, I'm not going to hard code something. I'm going to let the computer do all the hard work, because it's also going to double every 18 months. As long as I let the computer do the heavy lifting, we're fine. So that would be this, right? If I got a bunch of potatoes, I want a really good potato peeler, not something crappy that I'm going to suffer through. I want a scalable tool that works for large amounts of stuff. We don't care about speed right now, but normally speed is important. So if it's easier to throw things into a food processor, fantastic, great. We're not really worried about that, but there are some faster ways of doing for the code to run than others. And that would be a sign of a better snippet of code. Be correct. So that's where the nailed it comes in, right? Here's what you're expecting. This is what you get, right? It's wrong. Therefore, don't do that. Correct. Having your code do the thing it's supposed to do. That's good. Hard coding in values. No, bad, right? I can't change anything. I can't move things around at all. And then there's the be clear 2 weeks from now. And I couldn't find a really good cooking analogy for this one. So I went with a souffle. Because if I make a souffle and I can make it properly, there's still a really good chance that 2 weeks later when I'm making a souffle, unless the recipe's immaculate, unless the recipe is perfect, I'm going to screw something up along the way and it's not going to work. What I want to be able to do is make code that I can go back to later and look at it and go like, oh, that's what that thing does. Or I can understand what's going on there because people have to maintain it. So that was just the overview, right? That doesn't even give us to what our plan is or how we go about thinking through programming. This is just, you're going to make mistakes. Try and make it so that it's more generally usable code, that you're not doing something very, very specific. Try and make sure it works. And it goes line by line. So if you don't know how it works, go line by line yourself and see what it does. Here it's going to be this. Here it's going to be this. Here that value is going to be this. Oh, it's changing over here. That's what you're expected to do. So here's the plan. Before I code, I don't code. Step away from the computer. Don't code. Having done this mistake myself, still doing this mistake from time to time when I get arrogant and I go like, oh, I don't need to code that. So we're going to even hit one of those situations probably tonight. So first up, get a pad of paper. I actually am using a remarkable tablet, which is a tablet which acts like paper, looks like paper, behaves like paper. That's actually that's what you do. I doodle up my notes on that, but it's like using paper. Okay, I want to play with it, some examples, which is what I gave you in earlier assignments, and I want to keep giving you, right? What would happen if I did this? What would happen if I do this? So what would happen if I take 343 mod, so that percentage sign, 100? What happens? I get the number 43. I'm expecting you to try and do that. 343 divided by 100, what's the remainder? 43. 343 divided by 100, what is the number? 3. It's 3, remainder 43, right? Play with the numbers so you know what's going on. You can't code until you know what the heck the question is or what the problem is. That is also the thing they're testing in a Google interview. They'll ask you a question, and the first words out of your mouth should be questions about their question. You don't write out your solution or anything. You ask questions. How big is the data set? How is this? Like, what happens in this case? So I want to know what the problem is. I want to play with some examples. I want to have a really solid feel about this. I used to teach the same thing when I teach teach mathematical proofs at Northeastern. They'd be like, how do you know how to do the proof? And I'm like, did you play with the numbers? Did you play with the question? Can you give a counterexample? If so, walk away. You're done. Great. You play until you understand it. Then you go, what are my potential problems? What's the worst case scenario? Where can this hit the fan? Right? I want to think about all the different problems. I haven't done anything. This pad of paper kind of approach doesn't take you much time at all. It seems like it might take you time. It'll take you 10 minutes. You coding at 2 in the morning, take a couple hours and you'll be like, why doesn't it work? It's because you didn't think through all those possibilities. It saves you in the long term, much like planning your camping trip. Okay, you really need to understand the problem. That's it. Once you really, truly understand the problem, then you can go about, coming up with a solution. And does your solution handle all those things? I want to go from general to specific. And so I want to break down a problem. I'll start off something very general, and then I'll go, how do I do this part? How do I do this part? How do I do this part? What does this mean? How do I break it down into small chunks? My wife brought up when she was learning to program for the first time, I guess it's a Quebecois, maybe it's a Quebecois thing, I'm not sure. But, her computer science professor asked, so how would you get a robot to smoke a cigarette? I don't know why the robot has to smoke a cigarette. That's why I was kind of confused by that. It didn't seem very appropriate. Anyways, they don't breathe, so I guess that's fine for them smoking a cigarette. But how would you get a robot to smoke a cigarette? And people say, okay, well, you go and the robot reaches into the packet of smokes and pulls out a cigarette. Okay. How does a robot recognize the packet of smokes? How does it move its arm? How does it open the packet of smokes? How does it pull out a cigarette? How does it light it? How does it move its hand into its mouth? There's a ridiculous number of steps and a whole lot of ambiguity, and you can't have any of it. But the first step is the robot recognizes the pack of cigarettes. The robot reaches down, picks up the pack of cigarettes, opens the packet, puts a cigarette in its mouth, lights a cigarette. Okay, now that I have that, how do I do those 5 things? I go very general, figure out the solution. Don't worry about the details until later. Now, okay, how do I put a cigarette? How does the robot light a lighter to light a cigarette? What does it mean to light a cigarette? Okay, it has to have a lighter. Okay, a bunch of steps in there too. But I don't worry about that detail until I've done the bigger, and then I go smaller. Again, paper. I don't code because I don't know what I want to code yet. I don't know how I want to approach the problem. So I won't worry about the details until I've worked out all the high level, and then I'll work out lower level. I never actually explicitly write out all my code, the exact instructions, because I know how a for loop will work. But the general logic, I have all of that down before I code anything. I'll worry about the details later. That's why we did algorithmic thinking and pseudocode, because that's what pseudocode is. Big to small, figure out all the steps. I like to point out this. I'm going to be very immature here because it's a shout out to my friend Brad. So, you. The plan is, how would you do the problem? Right? What are the steps you would take? That's pass number one. How would you do this problem? I want to. We'll go over some examples, but I want to find the smallest number in a bag full of numbers. How would you go about doing that? How would you go about shoveling your driveway, or whatever the algorithm is? How do you do it? And there's the Brad reference because we're juvenile. We're like, your mom. He has a PhD in computer science from UBC and works at Google for the past 5 years. So he's not dumb by any stretch. He's juvenile at times, and he's a good friend because I'm juvenile too. How would you ask somebody who's not a technical person how to do this? How would you talk someone through this over the phone? Right? If I have your mom or your dad or your sister or whoever, and if they're not technical, how do you talk them over the phone on how to do a particular task? You can't make any assumptions. That's a lower pass still. You have certain assumptions when you're doing it. When you're explaining it to somebody else who knows nothing, you got to go really low level. That's what the computer's needing. So that's what the next step is. Once you can explain it to yourself, then can you explain it to somebody else who has no visual feedback whatsoever? Okay, so general to specific, and if you can explain it to yourself, then explain it to somebody else. That'll do it. But you can only do that when you talk it out, when you plan. And by the way, in case you're wondering, yes, this is me planning how I'm doing the lecture. This is one page of my lecture notes for how I was going to plan the lecture. You plan, then you do. You don't just start randomly making PowerPoint slides. Everything does this. It's just really important for programming. So, is this like anything else? Yeah, it's like a lot of other things. It turns out I have one skill in mathematics, one in total, that I've ever been good at. It was to the point that I was, my nickname is Stupid Smart Guy in my household. I don't think the smart guy part was in there at first. And then I won a math, or fourth place or something like that, but not really a spectacular win, but did really well in a math competition grade 9, I think it was. And then again in grade 11, only two times for one of those national math things. Not fourth place in the nation, fourth place in my school. Not spectacular, but okay. And the math teachers were like, what, this guy? This dumbass? What, how can he do math? The one thing I've ever been good at in math, or any kind of exceptional, is those geometric proofs. Proving that these two angles are the same, that kind of thing, where you're doing a series of logical deductions. That's the one. It is the same skill set. It's the exact same skill. Doing Sudoku, exact same skill set. That's what we're doing here. Methodically, deductively reasoning about the code, or how you would go about doing a series of actions in a methodical way. And you could probably see this in a bunch of other fields as well. Look around, see where else you apply this deductive reasoning, and how you fix your computer when something goes wrong. You don't just go, yeah. How do you fix if you're baking something and something doesn't work out? How do you fix the problem? How do you arrange, dinner meetings with a bunch of friends that can't get along, or whatever the case is? You do this all the time. So I want to go over a couple examples, see what we can come up with. So how would I go about using this approach? How would you go about doing something like switching two numbers? This is my personal favorite because it was literally what got me falling in love with computer science. When I saw them, oh, that's beautiful. Oh, and maybe you just think it's natural and you go, oh, it's obvious. If I have two numbers, how do I switch them? I can't just switch them. I can't just pick them up and move them. I can look at essentially one number at a time, right? So I have a number. Let's pretend I don't have any memory whatsoever, and I have a number on one board, I have a number on another board, and I need to swap them around. I can look at one, only 17, but I want to look at the other one. I don't remember the 17. So how do I solve that problem? It might seem obvious. Maybe it's not. But I want to play around with this. Can I start moving this number over to this? No, because I'll wipe out the other number. Can I add this number to this one? No, because I've modified this number and I can't get that number back anymore. Can I, what can I do? The answer is I get a third number, or third thing I can store the number on, transfer one number over there, then put this number on this one, and then move that number over. So essentially, I have a scratch pad. I have a temporary number here that I can move over. So A is exchanged with B. I make another variable C, and I put A into C. I then put B into A, and B into A, and then I put C into B. It's really nice when you think about it. You're like, oh yeah, that's the only way to really do it. How about this one? Let's imagine I have some text here. I just put some random text in here. Now let's assume, like a computer, like everything else, like actually how you read, I can only look at one character at a time. When I read those sentences, I scan character by character. Actually, I scan by blocks, but I'm looking for the letter O. How do I find all the O's in that sentence? So that means we need to think this through. How do I do this? Well, first of all, let's go back to, I gotta hopefully scan it very quickly. I'm going to be playing with paper first, so I'm going to have a bunch of examples. If I want the general approach to this, not for the word hello, that sentence, but for any sentence, I'm looking for any particular character. I don't know what the character is. I don't know what the sentence is. How do I do it? I get some paper out. I do a bunch of examples. I draw hello, how are you? I draw something without the character that I'm looking for. I want to find potential problems would be, can I find a character in an empty sentence? There's no words, just two quotes. What if all the sentence only had spaces? What if the sentence was only question marks? There's almost an infinite number of sentences you can put in there, but effectively, if I'm looking for what if I'm looking for a question mark in that sentence? What if I'm looking for the letter A? What about capital A versus lowercase a? Should that make a difference? I'm trying to understand the problem before I get going at all. So that's the first question I want to ask somebody. You're looking for the character A. Okay, uppercase or lowercase, doesn't matter. It doesn't matter. Okay, can the sentence be empty? Yes, it can. Okay, now I can have more of a plan. So I need to really understand the problem. I want to do a bunch of sentences looking for different characters, see if I can make sense of it. And you may already have the solution in your head, but that's why we do this, because some people think it's obvious, and it's no, sometimes you will need to go through this. Second thing is, I want to go from general to specific. So my tactic is I take my character and I look at all the characters, and when I find a character that I want to find, what do I do? I maybe return the position or something like that. Maybe we can look at other ways of doing it, but let's say I return the position of the very first character there. Or maybe I just have some kind of way of saying found one, or count the number of A's. That might be easier. So when I walk down my string, when I find an A, I increase the count and I keep going until I get to the end of my string. That's the first pass. What does it mean by walking down my string? Walking down my text? Going character by character? What does that mean? What does it mean my count? What does my count start at? Does it start at 0? Does it start at 1? What does it start at? What do you mean by increasing my count? Right? How do I compare A to this other character? Does it matter if it's capital or not? The details come up in subsequent passes when I go to specific parts. So I have a part for how I go from character to character, how I walk down my text essentially. And then I'll also have a part that I have to solve, which involves checking if the character is what I'm looking for at that position. That's it, right? So there are two different problems there. How do I check the character I'm looking for? at that position, and how do I go from position to position? And I'll worry about those details as I go. How would you explain it to yourself? Are you sure you understand it? How do you do it? That's that. My first pass is, how did I do that? Oh, I scanned down the text and found this character, and then I scanned some more and I found this character, and I've scanned some more and I found this character. And how do you explain it to your mom? Well, you'd have to explain what you mean by text. Then you may have to explain what you mean by go character by character, and including white spaces, and including tabs, including this, including that, because I don't want to skip over tabs in case I'm looking for a white space. Maybe that's the character I'm looking for, the space bar space. I could. Maybe I'm looking for capital A versus lowercase a. I need to explain it in more glorious detail when it's talking about to somebody else. Okay. How about removing all characters from a piece of text? What would be my approach? I need to figure out how to remove a character, first of all. What does it mean by removing a character? Can I just delete it? Can I just remove it? Or do I need to actually shift everything over? Right? I have to understand that part of the problem. But that's not the same as, part of the problem is going character by character over some text. Hello, how are you? I'm going character by character through this text. And every time I find an O, just say I'm looking for the character O. When I get to an O, I'm going to remove it. I'll figure out what removal means later. Then I go to the next character. Oh, I get to another O and remove it, whatever that means. And then I keep going. And then I can go into smaller and smaller detail again. How do I remove a substring S from the text? A substring is another piece of text within the text. So OW would be a substring of this whole thing. It is part of this main piece of text. It's a little piece of text in the text. How do I go about that? That's actually really hard to do, or conceptually, because I need to figure out the first character to the first character, and then I need to match subsequent characters one after the other until that entire substring, that entire OW, it matches up. And then when it matches up, then I get rid of that text. And then I move one character over and continue on. So it's character by character, and when I find a match, then I have to match all those characters until I make sure they're all matching, and then I can get rid of the text. How do I find, how to replace some substring S, some random, substring like OW? How do I replace it with something else like AL or question mark? So, hello, H question mark, RY question mark, W question mark dot, W question mark dot. How do I do that? Well, I have to figure out how to match that string, the OW, with something. And when I find it, I need to figure out how to replace those characters with the other characters, which is a whole other task. But I've broken it into something that's much, 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 much smaller. Scanning the text, matching the text, and only if it matches, then I remove the text. And removing the text is just another series of steps. If I have a number in a bag, how do I find the smallest number? Sounds fairly simple. It's not, but what do you do? So I put a bunch of numbers into a bag. I want to find the smallest number in that bag. I can't see the numbers. It's in a bag, presuming a, opaque bag. How do I go about doing that? What would you do? Well, what would I do? So I need to play with it. I'm going to put 3 numbers in a bag, see how I would do it. Put 4 numbers in a bag, see how I do it. What if I have no numbers? What's the smallest number in the bag if there's no numbers? Oh, I got a weird edge case. I got a weird case where things go really weird, right? If there's no numbers in the bag, what's the smallest number? There is no smallest number. So maybe I need to say the bag has at least 1 number in it. Okay, what if it only has 1 number in it? Okay, that's another scenario. I got to think through all these scenarios. I got to play with it. Then I need to figure out what my plan is based on what I would do. In this case, I'd pull off a number, look at it, pull out another number, look at it, and I will keep one number, the smallest one I've found so far, I'll keep it in a separate pile. So pull out a number, look at it. If it's a new smallest number, I'll put it in a special place and put the other one in the main pile. So I'm pulling off numbers and I'm just keeping track. I'm just keeping the lowest number that I have so far. When there's no more numbers in the bag, I look at the number that I've kept special on the side. I'm done. That's the algorithm for me. Okay, now I need to explain it to my mom. And that's a whole other thing, right? My mom's not all that technical. My dad's a doctor. My mom's a nurse. I was supposed to be a doctor. I didn't. I'm not supposed to be a technical person, but I'm the weird person in the family that does technical stuff. Right? How do you explain to somebody else how you'd find the smallest number in a bag? And the approach that you would take. How do you explain what it means by putting that number to the side? Okay. That was just the planning phase. And it's absolutely critical because the rest of the stuff is easy once you get the planning phase done. Honest to God. It's way easier. So the programming phase. We got a couple things in there. Again, we go general to specific. So when we later on, very, very soon at least, we'll be looking at prototypes. Prototypes, that all the fancy pants word for this is what the function is going to look like when I finally get around to defining it. That's it. I'll eventually get off my ass and define this function, and it's going to look like this. I'm going to eventually get around to building this thing. It is essentially, this is the scaffold. It's the sketch. I'll get to it eventually. Yeah, it's going to happen. And maybe what I want to also do at the same time is write the function or write the code just enough to get this thing to compile, just enough to get this thing working. It's not actually working at all. This is like a cardboard cutout. You know, it's some crappy thing you're putting together just enough to try something out. So if I want to see how my website works, I put the minimum stuff in an HTML file, put it onto a website, see if I can see it before I go fancying it up and making it all clean and making sure it all looks all pretty. I want to just the minimum amount, right? See if it works. That's the first step. I go general, and then afterwards I will define that other stuff. So I have the outline, I have the format, I have the structure of my program, and now I fill in the little gaps. I fill in this function, then I fill in this function, then I fill in this function. I'm going to do each part by part, bit by bit. I should have said bit by bit, I think. I might have said it somewhere else. I'm just doing one little part at a time. I don't do all of it at once. I sure as hell don't code everything for an entire assignment and then go compile and see if it works. It's the stupidest thing you can do. I've done it enough times. It's stupid. Don't do it. Learn from my mistakes, right? You do a little bit, fix it, make sure it works. The minimum amount. Compile it, test it. Another minimum amount. Compile it, test it. What you don't want to do is sort of, there you go, build the bookshelf all the way through to the very end and then look and see if it worked. Do a little bit, make sure it's done right. If I'm putting up shelving, I'm doing the level, I'm checking the level, like whether it's flat or not, horizontal or not. I'm checking the level of that shelf, every single shelf I put on there. Because if it's not level, I got to start that part over again. If I build an entire bookshelf or build something all the way through and then afterwards go like, hey, did that work? Nope. Okay. Back to the drawing board. Like you would never do carpentry. Like you would measure something twice, then cut it, then test to make sure it works. Then move to the next board. I don't just randomly put down boards and hope to God I get something in the end. So, do it part by part. The comments, when you put them down, they're for you and they're for the TAs. They're for other people. They're not for the compiler. They're not for the computer. They don't care. They're for you. And I remember my boss a long time ago would say, like, when you don't know what that comment means anymore, or when you don't know what that code does anymore, then you can get rid of it. But comments are like 3 months, his promise was, and he was right, It's like about a month from now, when you look at that code, you will have no idea what it does. You'll purge it from your head. You might remember some parts of it, but you'll have to refigure it out. And when you do, you will want to have that comment to say exactly what it does and for you to understand it. It's just notes for you. So you go like, oh, that's what I was doing. When I do a recipe, I'll put little notes to see like, oh, that's what this thing means, if there's something that's confusing. And like math, like playing the piano, like anything, playing a sport, if you want to laugh, watch me play basketball or any sport actually, right? I'm terrible because I don't practice. You don't get good at basketball or hockey or anything unless you're practicing. I'm walking around with my kid skating and I'm barely skating on the ice, and you see all these dads that are like, you could tell they were playing hockey on the side all the time, right? That's not me because I don't have any practice. It only comes with practice. That's what this is for. That's what the assignments are for. That's what the labs are for. If you don't know how to do it, it means you didn't practice enough. If you get to that exam and you do not know the syntax, it's because you didn't practice. You're not memorizing the syntax. You type enough, you'll know it. If you don't know it, you can look it up easy enough. It should feel very comfortable after a while, but it requires you to just get into the salt mines. Okay, so we're going to go over an example. We're going to have to get in advance of this thing. We're going to look at loops. We're going to look up a slow way of doing loops for factoring. In fact, I'm going to find the minimum factor of a number. I keep on using this example, and I apologize in advance. You'll see it all in other places in the course, simply because it's a nice little example. Factoring is something like I got used to playing with numbers. So factoring is any number, any positive number over 2, a positive integer. So it has to be a whole number. Any positive integer over 2 or more can be factored into a series of prime numbers, uniquely factored into a series of prime numbers in ascending order. Meaning the number 5 is 5 and 1, right? There's no other number. It's a prime number. 6 can be broken into 2 and 3, 2 different prime numbers. They actually uniquely identify the number 6. 8 is 2 times 2 times 2. It's the product of these prime numbers gives you that number. There's no other prime numbers that you multiply together that will give you 8. It's 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. It's a series of prime numbers. Those are the factors of the number that we're dealing with. So if I'm taking the number 15, what I should get is 3 and 5 are my prime numbers, are my prime factors. It's called prime factorization. So take any number, 17, it's a prime number. The only number that the prime factor is 17. If I have a number like 18, their prime factors are 3. I guess it's 3 and 2? 3 and 3 and 2? Yeah, 3 and 3 and 2. So 2 times 3 times 3 would be the unique order. I want to play with the idea to make sure I understand that question. What does it mean to factor something? What is prime factorization? It means the series of prime numbers that I multiply together to give me this number that I'm looking for. Okay. So I want to do a bunch of examples like I just did. I want to think about how I'm going to go about doing this. If I want to find the smallest prime factor of a number, what do I do? Well, I'm going to start off at 2 and check 2. Is 2, I don't care how I do it, I'm going to start off with 2. Is 2 a prime number? Yes, it is. Okay. Is it a factor of whatever number I'm looking for? Let's say 18. Hey, yes, it is. I'm going to stop. How about, let's do 17 now. 2. Is 2 a factor of 17? No, it's not. How about 3? No, it's not. Now, I could say, how about 5? But it's hard to figure out the next prime number. So let's just see, how about 4? If 2 is not a prime factor, 4 certainly isn't. It's 2 times 2. Okay, so no, 4 is not. How about 5? No. 6? No. 7? No. 8? No. All the way up to 17, and I'll stop there. Let's do 3. Let's do 9. Okay, 9, is it divisible by 2? No, it's not. That's effectively what I'm asking. Is it divisible by 2? And divisible by some number? If it is, it means that number is a factor. That number multiplied by some other number gives you that original number. Another thing for me to figure out. So is 2 a factor of 9? No, it's not. Is 3 a factor of 9? Yes, it is. 9 divided by 3 gives you 3. No remainder. We're good. Okay. So I have a plan of attack, I think. I'm going to take my number. I'm going to start off with, let's say 2. I can start off with 1, but it's always going to give me say true for 1, right? 9 divided by 1. Well, there's no remainder. 17 divided by 1. Well, there's no remainder. I need to start off at 2. Okay, so I'm going to start off at 2, and then I'm going to test 3, and then I'm going to test 4, 5, 6, up until, when do I stop? I'm going to keep it simple. So I'm going to stop when I get to the number I'm looking for. I'm not going to try and stop at halfway or anything like that. I can figure that out later. I can clean it up. But the first brute force ignorance way of doing it is just test all the numbers until I get to the number I'm looking for. That's it. That's my plan. And then I would explain it to somebody else for it. But I want to see this in action. So let's see this in action. Okay. Smallest factor of a number. Okay. Okay. What does that mean then? So I need to figure out this. What does it mean to be a factor? I happen to know what the answer is, but I would play around with a bunch of numbers. How do I test to see if 9 divided by 3 9 evenly divides 3? Actually, we've already done that, haven't we? So I'm going to make some silly little function here, and we'll get to functions soon, but this is my main method. I'm going to find factor, and I'm going to pass in some number. We can't do functions yet, but we'll look at this. So the function I'm going to be looking at is 9. And I want to have, I'm going to make some variable, then we're going to test in here. Okay, I'm going to need a function called find factor. Okay, it's going to return the first factor, okay, and it's going to take in some parameter, or maybe call it 2-factor, the number I'm going to factor. Okay, I'm going to do, here's me programming this thing. I'm going to return 0, or let's say return 2-factor, maybe even better. There we go, and that's about it. And maybe I'm going to printf the smallest factor of 9, and maybe I'll use as a variable int test1. I'll put some random number in here. Why? Because I sort of want to be able to change this one number here and test it for a bunch of things. The smallest factor of, it should be an I, is, I'm going to put another number in here, I. I'm trying to do the minimum amount that I can do to test this thing. Just absolutely minimum amount of stuff I can do to test things. It's going to be wrong, by the way, if you hadn't noticed. Oh, and I also, what's wrong with this thing here? It says this. We'll get to debugging in a second. Actually, let me leave it alone for right now. Okay, I'll debug it in a second then. Okay, so let's go back. Hopefully. Anyways, okay, so I do part by part. I do a bunch of comments. Oh, and there's my refactoring, right? And then I need to fix things. I wanted onomatopoeia. I wanted alliteration. So, plan, program, patch. That's the only reason, right? It's testing, debugging, and not doing it at the end. It's not a side effect. It's not something you do at the very end. It's the thing that makes sure that you know it's working. So first things first, I'm going to write a small amount of code and see if it works. Make sure it works. Make sure it compiles. Make sure I can see stuff. Then I'm going to, if there's an error, I'll see the arrows on top when I go to compile it. And I will work from the top down because the top arrow could be causing all sorts of errors afterwards. It cascades. The first one causes this like avalanche of errors. So I'll just work on the first error, fix it, try and compile again. Next error, fix it, try and compile again. Next error, fix it, try and compile again. I can just keep on just plugging away, stopping errors along the way. But I have to start at the top because if I fix ones on the bottom, they might be errors because something at the top is broken. I could be making matters worse. I start at the top, work my way down. Okay. We have breakpoints, which I've already looked at a little bit, but they're your friend. I keep on seeing my 2400 students or my other students over the years just trying to avoid them. Do not avoid them. They are saving grace. I avoided them for years. Maybe not years, but I avoided them for a while, and then I was finally forced to use them. I'm like, oh yeah, that's why you use them. It allows you to stop your program, look at what the data looks like, then turn them off and go again. They're beautiful. Okay. They're relatively easy. You click the side. Okay. You can also do what we're about to do. Output. Do a printf statement. See what you get. Is it right? Nope. Fix it. Right? Just have some kind of output that you can look at. If you hadn't noticed, every single video game has this. Has some kind, like there's a debug mode that they'll have somewhere in there that you can, or most of them have this, where you can look at what the frame rate is or some other information. Because the programmers needed it. All of this is deductive reasoning. So I want to have something where I have a plan, what I expect to see, and then I test that. I don't just randomly put things in there and randomly guess what the output is. I plan what I would expect to see, and if I don't see it, it means my mental model's wrong or something's wrong. And then I can fix it. But if I'm just randomly guessing, I can't fix it. I need to have if I put the number 9 in this thing, I would expect the smallest factor to be 3. Okay, if I don't get 3, well, then I know I have something wrong with my code. I can write a whole lot of test code, even if I'm not going to use it right away. Just write test code to test how things work, and if I need to, I can comment it out or delete it or whatever the case is. In fact, just comment it out. I would love to see this test code. You're just trying to kick the tires, make sure it works, right? You don't drive, if you're not worried about the tire pressure, let's say kick the tires, right? If you're worried about your tire pressure, you don't go driving on the highway. You go to a pump and you check the tire pressure. Then you can drive on the highway. You don't just randomly I hope for the best. You test a little bit at a time. And right back to what we were doing before, you expect errors. You say nothing that says nothing about you. It is not you. It's the nature of the task you're doing. Everybody screws this up. There's always some kind of error. And you go, oh, how do I solve this problem? Oh, how do I? And you just work through it incrementally. And then you fix those and you move on to the next thing. So we're going to go back to the factoring thing. I think this is actually my last slide. So that's my last slide. So let me just go back to my factoring. We'll work through this. So first of all, I have an error. If I want to, I can Control-Shift-B, see how it compiles. It's not going to compile, by the way. Hey, printf is not found. Why? How do I'm missing print? I didn't write a ton of code yet. So I know it's not some other weird thing that's happening. I didn't write much. So let's figure this thing out first before I write more code. Wasn't there a bunch of include stuff? So I'd go to what I've given you before, but I happen to know, and here we go. We had this kind of thing. Standard IO, and I'm hoping that's going to be the right one. Half the time I'm wrong. I forget what the thing is. Hey, the error went away though. Good enough for me. Okay. Does the code actually compile? Okay, the code actually compiles. Let's see what happens. What do I expect? I have the number 9 going into this function. Find factor is going to find the smallest factor of 9. It's going to return it and put it in here. Maybe I should call it fact test because I'm going to be trying other things. There you go. I like having good names for my variables. So I'm going to find the smallest factor of 9, and then I'm going to, okay, we got to look into that thing, the virus scan shenanigans you guys talked about. I might be still having. Okay, so I'm going to find the smallest factor of 9. It's going to be in here. What would I expect to see? I would expect to see the smallest factor of 9 is 3 and a new line. That's what I expect here. Nothing's run yet, but let's run it. Okay, it's compiled as well. I got to move that over. Okay, let's have a look at what I have here. All right, smallest factor of 9 is 9. Wait, that's not right. Oh, wait. I expect an error. I had a compiling error first, but now I have a logic error. Still need to fix it. I'm going to make a little change, fix it, and then move on to the next part. I'm going to try and fix it and move on to the next part. Over and over again. I'm going to do I didn't do this part yet. This find factor part. Okay, now I can do that part. The code works though. It runs. It doesn't give me the right answer. So now I'm going to work on this part. If there was another part after that, I work on that other part. I do a little bit at a time. Clean it up, make sure it runs, make sure it compiles, test it, move on. And so what I want to be able to do is keep testing different things. So I'm going to test other things as well. So maybe what I want to do is, okay, let's do, I can manually do this a bunch of times, but I don't want to. I'm lazy. So we could do something like, I'll have to just show you what this looks like. I'm getting ahead of myself a little bit, but not really. Okay, I'm going to use a loop. We'll get to loops. And you might wonder why I'm starting at 0. I'm going to always start at 0, at least for this case. Less than 10. Actually, I'm going to leave this off for the time being. I'm just going to comment it out for right now. I want to fix this other thing first, and then I'll test it a whole bunch of different times. I want to test it once with the number 9, see what happens. Okay, I will still need a loop. So what am I going to do? I'm going to start off at the number 2, then I'm going to test 3, then I'm going to test 4, 5, 6, up to, technically I'm going to go up to 9. But what I don't want is to put the number 9 here. Because if you pass another number into this thing, let's say 10, it's not going to work. Or it may not work the way you expect it to. If I pass in the number 5, it's not going to work. It's going to go past the number, the maximum number it could be. What I want is this sort of to drive how many times I'm going to be testing numbers. So I'm going to start at 2, then 3, then 4, up to whatever that number is. That when I get to the number that I'm trying to factor, when I get there and there's no factors, I know it's a prime number. I just return it. So, by the way, I'm also going to want to test a prime number on this thing. I'm going to want to test like a negative number on this thing to see if it breaks. I'm going to want to test like 0. I'm going to want to test 1. I'm going to want to test a whole lot of different numbers. So we'll do that in a second. But here we go. I want to let's call it current number, set it equal to 2, and I need to figure out how we figure out if something is a factor. So let me just do my loop here for can I do that directly? Let me think about this before I start typing stuff. What I want to do is this is going to be a loop here. I know how to write the code, but I'm trying to figure out how I want to say it out loud. While current number is less than 2 factor, that'll do. I want to check if current number, oh, I got to figure out, let's just put it there, if current num is a factor. I'm going to just put a comment in here. then I'm going to return. Then return that number. I'm going to just stop what I'm doing. Otherwise, if I get to the end, I get to current number is equal to that number to factor, then I'm going to return the number to factor. If it's, let's say, a number like 7, the current number will eventually become 7, and then I'm going to stop. I'm going to return 7. That's what I want. Okay. I also need, every time through this loop, I need to go current number is equal to current number plus 1, right? I need to increase that number each time. There are other ways I could write that. I could write current number plus plus. I could write current number plus equals 1. There's a bunch of ways. It doesn't matter. I want the thought here. I can clean that up later. So I'm going to start at 2. Then I'm going to increase by 1, increase by 1. Heck, I can still do this. I can still run my code. Let's do that. Is it going to work? Yeah, it's going to work. All right. It's going to start at 2. And as long as to factor is not, okay, that actually, this might actually be better than I was originally planning. So let's try. Anytime. I gotta move this over again. The smallest factor of 9 is 9. Well, of course it is. It didn't. There was nothing to stop my loop. I went from 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10 to 9, and then I stop. If you don't believe me, we can put a for loop. We can put a printf statement in here to see what it looks like, or we can do this breakpoint. I just clicked on the gray box. I press play. It stops right at that line, and I can see, hey, current number is equal to 2. After the next line, the current number is equal to 3. The current number is equal to 4. Current number is equal to 5. Current number is equal to 6. It's going to be equal to 7 there. 7, 8, 9, and then stops. Okay, so I can test my code. I can make sure that that part works. And now I need just some way of stopping this thing when I get to the end of, when I get to a place where I want to stop. Okay, how do I figure out if current number is a factor? So I got to figure out that thing now. Okay, what's my approach? Well, we did something similar to it, right? We talked about remainder. And if it's evenly divisible, right? So if it's evenly divisible, then it doesn't have a remainder, right? So what if I did this? If, let's see, 2 factor and is divisible by current number. Oh, well, that's not going to work either, right? If it's 9 and 2, it's going to 9 divided by 2 is going to be 4, and with remainder 1. Oh, I need remainder. Okay. So if there is no remainder, stop. We'll look at all that syntax in a second, but that's all we're doing. If there's and since we're starting at 2 and moving up from there, it's always the smallest factor we can come up with. All right, let's have a look at this, and I'm just going to run it and see what happens. All right, let's find out. Hey, the smallest factor of 9 is 3. The sentence structure also works, so I don't have to fix that at all. Great. Lucky, but great. Let's do something else then. I said I was going to do this, so let's do this. I'm going to start off with, I'm going to make it start off at -2. I'm going to go up to 10. This is advanced stuff when we do loops. In case you're wondering, don't worry about not knowing this yet. There's only so many things I can do without loops. It's really quite limiting. Okay, I'm going to make a number. I don't want it to be 9 each time. What I'm going to do is like test is equal to I, let's say. So it's going to be -2, -1, 0, 1, 2, 3, 4, up to, but not including 10. So it's going to be -2. I can put it as a comment. I is -2 up to 9. Up to and including 9. Okay. I'm going to set that value. I'm going to pass in the value in here. So I'm going to see what the factor, the smallest factor of -2 is, and the smallest factor of -1 is, smallest factor of 0, smallest factor of 1. I want it to work in all of these cases, and I don't know if it's going to work in all those cases, but what would I expect? For me, at least, I'm going to say if it's below 2, I'll return the original number. Why? Because what else would make sense, right? You're trying to factor a negative number. It doesn't make sense to factor it. You don't factor a negative number. So any negative number, you try and factor it, I'll just return the original number. That's what I would hope. That's my hypothesis. And so what I would expect to see is -2, -1, 0, 1, 2, 3, 2, 5, 2. So for 6, the smallest factor is 2. 7, smallest factor of 8 is 2. Smallest factor of 9 is 3. And then I would stop. And heck, what the heck, I'm going to do 15. Oh, it compiled. That's a small miracle as well. If I was missing something like, I don't know, this, I want to find it. Something happened. Oh, what the, look at all these errors. Look at all these errors. It's expecting a semicolon here. Let's see. Fixed. That's why you start at the top and you work your way down. Okay, so let's run this and see what happens. Small factor is -2, -1, 0, 1, 2, 3, 2, 5, 2, 7, 2, 3, 2, 11, 2, 13, 2. Notice every second one is the smallest factor is always 2 because it's an even number. And for other numbers, you'll get other. And so if I went to 15, you'll get a 3 in there. If we went up to 21, you'll get a 3 as well. But you'll get. Let me think of what numbers we would have problems with. Oh, let's find out. Let's go up to 30. Then I can test out more numbers. Yay. All right. Smallest factor is, other than that, I should have a 7 in here somewhere. The smallest factor of 7 is 7. Smallest factor of 14. Oh, wow. There's really no 5s. 25 should be 5. There you go. That's the next time where there's a smallest factor that is not 2 or 3. That is not a prime number. Right? And you could try out a whole bunch of numbers and see what you get. Okay. That's what I wanted to go over for today. I know I went way longer than I expected. My wife's probably wondering what the heck I've been doing. It's like a 2-hour video or something. But this is what the thought process is when I'm going to code. I'm breaking into small chunks. I'm explaining it to myself. I'm playing on paper. I'm planning. I'm doing a little bit at a time. I'm compiling. I'm testing. I'm doing a little bit more compiling and testing over and over again. The worst thing you do is to dive in and just start typing. It is the kiss of death. You plan, you think it through, you break it down into small steps, figure out what you would do, and then figure out how you can make it general, that it works with any number or any input. What are the inputs? Where could things go terribly, terribly wrong? And then figure it out from there. Okay, so I'm hoping this was somewhat useful in some way. I'm trying to find the methodical way of talking about programming and the approaches that you take, because it's not something it's not cookie cutter approach, but it's not a mystery. We have best practices that we do because we know we make mistakes. They will happen to everybody. It is not about you making mistakes. It's not about me being dumb, I can't figure it. No, you got that. Do a little bit at a time, and eventually you figure out each of those steps. But if you try and bite off more, like try and do a whole lot at once, it's really oppressively hard to figure out what the problem is. So a little bit at a time, and you can go through much faster than trying to do all at once and then trying to figure out what went wrong. And if you don't plan at all, you're really screwed. So with that being said, I'm hoping that was useful for some of you. Thanks, everyone. Have a good night.